Okay, here's warm-up 4.7. All right, we've got this function here. First question, how many zeros are there? Well, the amount of zeros is going to be the same as the degree of the function. So this is a third degree function because the highest degree term is 3. So that means that there are going to be 3 total zeros. Just because, oh, I need a pen that works. Just because, there we go. This is third degree, okay? All right, so let's list the possible rational zeros according to the rational root theorem. Well, the rational root theorem says that I can take my possible rational roots are going to be the factors of this, which is my p, over the factors of this, which is the q. All right, so my constant, that's the term without a variable. So I'm going to look at the factors of 4 over the factors of 1. Okay, so let's think about everything that goes into 4. Well, 1 goes into 4, so does 2, so does 4. But actually the negative versions of all these go in as well. So I'm thinking of all of the integers, positive and negative, that go into 4. And then all of the integers that go into 1 are just 1 and negative 1. So these are my possible rational roots. Okay. So if you're multiplying or dividing by 1 or negative, or sorry, if you're dividing by 1 or negative 1, that means we're really looking at these 6 different integers as possible rational roots. Okay. So it doesn't mean that all of these are rational roots, but if there are any rational roots, they have to be in this list that we just made. Okay. So trying to factor this equation, to me, the first thing I would try if I'm just factoring it is factoring by grouping, since I have 4 terms. There's no common factor that goes into all 4 terms, so then I'd try splitting it up into 2 groups. And both of those groups, you would, like the first group you could factor out an x, the second group you could factor out a 2, but you're going to hit a dead end with factoring by grouping because there's not going to be any matching factors that I can factor out after that. Okay, so that's a dead end. I'm not going to go down that road. So what I'm going to do is try to use some of these rational roots to start breaking this up. Okay, so I'm going to do some synthetic division and see if I can get 0 remainders. If I get a 0 remainder, then I have a rational root here. Okay, so then I'll have a factor. All right, and there are 6 different options to try. So if you didn't have a calculator, you could just try out all 6 by dividing and seeing if you get 0 remainders. Just as a little shortcut, and I know we are going to graph this on the last problem, so it's a little weird, but I am going to graph this on my calculator because I'm looking for x-intercepts. The x-intercepts are going to be the roots. So I hit the y equals button here, and I've already got this typed in here, but there's that function. And then I'm going to hit graph. And then when I do that, I can see, okay, it looks like negative 1 is an x-intercept, and that is on my list here. So that's the one that I'm going to try. I'm making a guess here. I'm guessing that x equals negative 1. I don't know that for certain because it could be that that x-intercept is negative 1.1 or something like that, and isn't a rational root at all. So I still want to verify this. So if negative 1 is one of my zeros, then I should be able to factor out x plus 1, okay? So I'm going to divide that, that polynomial by x plus 1. I'm going to do this with synthetic division. I'm checking there's no missing terms here. It's x to the third, x squared, x to the first, and a constant. So I'm just going to pull out the coefficients there, okay? And then I'm going to do the synthetic division and see if I get a 0 remainder. So I'll pull down the 1. Every time I get a number down here, I'm going to multiply it by negative 1. 1 times negative 1 is negative 1. Then I add these. 2 times negative 1 is negative 2. That goes right there. Add those. Multiply again and add. And I did get a 0 remainder. So that tells me that my guess was correct. Okay. So now when I think about what I've done to the original equation, well, I factored out x plus 1. Because is zero product property, that would mean x would equal -1 if f of x was 0, right? And when I divide out the x plus 1, what I have left is this trinomial here, okay? So this would mean x squared plus 2x plus 4. So you have to be a little bit familiar with synthetic division to be able to do this, okay? And then I would look to see, well, I factored it a little bit. Let's see if we can factor this trinomial further. So I want to see if, I'm going to use a diamond problem here. I'm going to put the 2 on top and the 4 on bottom. So I'm looking for two numbers that add up to 2 and multiply to 4. Well, a 1 and a 4 is not going to work because they won't add up to 2, and neither will 2 and 2. So that means that this diamond problem doesn't have a solution. That means I can't factor this any farther. Okay? So now the next step. So I already know that one of my zeros is -1, but wait a sec, there were supposed to be 3 different zeros, and I only know one of them, and I can't factor this any further. But that's okay. So what I'm going to do is use my work from the previous problem. I factored this as much as possible. To find the zeros, I'm plugging in 0 for y and then solving for x. So zero product property tells me, okay, if x plus 1 equals 0, x equals -1. I already knew that piece because I verified that down there. The other 2 zeros are going to come from setting this trinomial equal to 0. Okay, so even though I can't factor this, I can still solve for x. So when I can't factor, my backup plan is, well, I've got 2 backup plans, either quadratic formula or completing the square. So I'm going to complete the square here. I'm going to try to create a perfect square trinomial. So I'm going to need a different number there instead of 4. So I call this the mystery number. So I'm going to move the 4 over to the other side of the equation. I'll leave a little blank spot where the 4 was. So I moved the 4. Okay, I'm going to be adding something here to create a perfect trinomial. That's my mystery number. And I have to add the same thing to both sides of the equation. Okay? And then I'm going to use a little formula here to find the mystery number. And that's going to be b over 2 squared. Okay? So b over 2, well, b in this trinomial is 2. So I've got 2 over 2 squared. That's 1 squared, and that equals 1. So that is my mystery number. So that's going to go there. It's also going to go there. Okay? And now on the left side of the equation, I've got a perfect square trinomial, which means it's going to factor into something times itself. So if it factors into something times itself, I should be able to write it as x plus or minus something squared. Okay, and you can set up a diamond problem or something here, but this is going to be double 1s, right? So this would be x plus 1 times x plus 1. I want to write that as x plus 1 squared. On the right side, just do the arithmetic there. And the point of this is now that I can take the square root of both sides to solve for x. So when I take the square root of both sides, remember you need a positive and a negative root when you take the square root of both sides of an equation. The x is almost isolated. I'm just going to subtract 1 from both sides. I'm going to slip that in front of the square root. Okay, and then I wouldn't want to leave in a final answer a negative under and a radical underneath the square root, so I'm going to write that as I root 3. Okay, so this is my other 2 zeros. There's 1 0, there's the other 2, because I've got the plus and the minus. And that's why I couldn't see these x-intercepts, because they're imaginary. They don't exist on an xy plane, but because they're imaginary. Okay. All right. And then let's describe the end behavior. So the end behavior describes what's happening at the 2 ends of my graph. Okay. And so I can figure this out by thinking of the simplest possible equation that has, so here, let me write my equation here. X to the third plus 3x squared plus 6x plus 4. So I want the simplest possible equation that has a positive leading coefficient, like this does. So I could use 1 as my leading coefficient, and I want it to have an odd degree. And so this has those same attributes, positive leading coefficient, odd degree, because it's raised to the first, okay? And then if you know what this looks like, it's going to be a line that goes through the origin with a slope of 1, something like that, okay? And this function is going to have the same end behavior. So I just need to, what's happening on the two ends? At the far left, it's going to be going down. At the far right, it's going to be going up. So I'm going to say as x approaches negative infinity, so that means as we're going left on the x-axis, we're going to go down on the y-axis. So as we go left, we're going to go down, okay? And then as we go right, we're going to go up. So as x approaches positive infinity, y is going to approach positive infinity. Okay? Now, we're going to put all of this together to sketch a little graph. It says no y-scale necessary, and that means, well, I'll get to what that means in a second, but there's my x and y axis. So I know that I've got a 0 at -1, so that's an x-intercept, okay? And then I'm going to use this end behavior. So so it's going to have the same end behavior as this. So it means I'm going to start if I'm drawing my graph from left to right, I'm starting it down here, and on the other end, it's going to be going up. Okay. Now I already graphed this on my calculator, so I have an idea of what it looks like. But even if I hadn't seen it on a calculator, I would know, okay, it crosses the x-axis here, and it's going to be going down towards this end, and it's going to be going up towards that end. And this is, I'm just putting those two things together, so I don't really know exactly what's happening with my curve other than where it starts and ends and where it crosses the x-axis. Okay? All right, that's the end of the warm-up, and I'll see you next time.